Um, Today, I want to read the paper written by Witten, which studies the correspondence between the GT gravity and the matrix integral. And in 2019, people found that the how to say the pure GT gravity is due to a matrix integral. Yes, from the ADS safety view, we can see that the ADS2 space is due to the CFT1, and the CFT1 is just one-dimensional quantum field theory. One-dimensional quantum field theory just has the time, there's no space. It's just the quantum mechanics. But something amazing is that the ADS2 gravity, the gravity in ADS2 space-time is not due to a certain quantum mechanics system, but to the ensemble of quantum mechanics. And we know that a quantum mechanics system is described by its Hamiltonian, and this system is proved to be described by a random information matrix. So it is described by the matrix ensemble. So this is the measure, and this is the potential. And H is L times L Hermitian matrix. You need to notice there is AL. Okay. Then this is just the GUE ensemble. This is one of the beta Dyson ensembles, that is beta equal to 2. Okay, when you can write the measure of the matrix with its eigenvalues, that is this one, and you can find this is squared. This is the power is 2, so the power is just the beta. Okay, then this is the potential. Okay, that's great. Okay, then our target is to calculate the correlation function. But for the matrix model, what we want to calculate is just the trace HK, or something like this. We want to calculate this. We can denote a generating function for this thing that is R. That is called R. Let me see it here. But before we do that, we just consider to write and to consider that this factor contributes to the effective potential. We can write it as an exponent, just like this. We just use log. I'm sorry, this is here should be a square. Okay, that's great. Then we define the density of eigenvalues. It should be denoted like this. Sorry. We need to denote. We need to use the 0 index to means that we have normalized it, so that this condition holds. Okay, that's great. When L go to infinity, there's so many delta function will contribute to a smooth function. Okay, and this reason, okay, I think it's called, sorry, a solvent. This is the solvent. So it's solvent. You can just expand it. It should be, let me see, is x k plus 1 hk trace. Yes, this is the generating of the trace hk. That's great. Then you can just write it with the eigenvalue. Great. Maybe someone want to calculate the expectation value of the potential, of the density of eigenvalues. That is, we may want to calculate the expectation value of the density of the eigenvalue distribution. This is we first we want to know, okay, how to calculate it. This is the first question. And we will find that the solvent is related to the density distribute the eigenvalue density. I checked that if I have made a mistake, the pronunciation of the reason. Okay, resolvent. Okay, resolvent. Okay, maybe I need to call it a resolvent. Okay, this is a resolvent. This is the density of eigenvalues. Okay, you need to write an expression of the delta function. It is well known. We need to consider that what is the definition of the delta function. Okay, this is wrong. Sorry. We need to consider the definition of the delta function. Delta function is defined as some like this. That is, for an arbitrary function f, you do the integral from minus infinity to the positive infinity. You will get that f0. Okay, then you can make use of the residue series. That is, you can construct a function with a single pole at I epsilon and minus I epsilon, and with residue equal to 1. Then you consider use this function. This part plus this part times fz. Then you need to integrate fz along the complex plane of x. Okay, if you can always choose this contour or this contour. Anyway, you like it. You may assume that there is no other pole of fx. So you can find that this contour plus integral is equal to take the residues at its pole. So it is just f I epsilon. For epsilon go to 0, it's just f0. So it is this thing can serve as the definition of delta function. But here I mean the question is if fx is some function with some poles. For example, the fx can have other poles on the complex plane. Then how to fulfill our discussion? Maybe you can just to direct check it. That is, you can just write down this function. It is a real function. Okay, like this one. You can just write it, and you can find that its integral is equal to 1, and its support is just located on the neighborhood of x with the width of the word epsilon. When epsilon go to 0, it's just as a picture. It's just as a picture of the delta function. So maybe you can just from this perspective of view to discuss. This is nothing I want to. This is nothing more I want to discuss. Anyway, we just use it as you use this one as a definition of delta function, so that you can write the normalized distribution with this one. There's something happened. No, nothing happened. Anyway, we just use this as a definition, and you can just rewrite the normalized density. It is equal to, okay, this is the delta function. That's good. Then you can find this one. You can this is a summation of all lambda or eigenvalues. So it's just as a definition of the solvent. Yes, the solvent is defined on x plus epsilon and x minus epsilon. This is just the discontinuity of the solvent. Okay, so you can see that maybe okay, let me see here. Well, this is rho. Sorry, rho equal to this one. So the density is equal to the discontinuity of the solvent across the real axis. That's great. Then what can we get from this definition? And we can just write Rx as okay. First is a summation, then you can write it as an integral. It's great. So what can I get? I want to try to calculate it. Maybe it is not so easy. But at first, we need to we need to we need to think that what we have in hand. We don't know what is density, what is the what is the solvent. We just have the form of the potential. Okay, we just know the expression of the potential. How to got the density, how to got the solvent from the potential. This is the point we need to. This is the problem we need to solve. Okay, so we need to find the relationship between the potential and the density of the density distribution. This is we can just write the effective potential as this one. Let me see if I have made a mistake. Okay, no mistake. No mistake. Okay. Okay. Then it should become what? Here we can just write this one as this one. Okay. And this one, oh, if you want to just write it through the definition of zoo, it makes some it looks some not so good. But anyway, we can just write it this. And we know there is a large L as as a factor in front of the effective potential. Okay, the effective potential we need to use. Sorry, we need to let me see. We need to write L here. Yes, there should be another L. Okay, we want to the we want the rho lambda is a stationary distribution, which means it any perturbation around it will make that the delta the change of the effective potential is 0. Okay, so we just get this one. Okay, lab. Okay, should be L maybe. That's great. Due to there is a denominator L, so we can replace the rho with the nominator rho distribution. Okay, that's good. This is what we have. Then what can get? I have nothing to do. Maybe. It seems that we cannot solve this equation. Yes, cannot solve this equation. So what happened? So it seems very hard. maybe, let me see. Maybe we do need, but when I see the paper, they don't do like so. What they do is just to write the effective potential. And that means it just to write the matrix and symbol as this is lambda I, di. This is the value of the eigenvectors, eigenvalues. Pretty easy. Then this one is minus L, and the sum of I, V, and I vector. So if you write the matrix symbol in the form like this, we have that effective potential should equal to L V and I, then minus what? Why is a minus? Let me see. Yes, it is a minus. Yes, it is minus log lambda I minus lambda j square. I is not equal to j. I'm very puzzled. In the original form, we have it is lambda I minus lambda j square, I less than j. Okay. Then we can write this to exponent. It should be log lambda I minus lambda j square. Nothing happened, I think. It's the sum of I minus j. I is less than j. So why we reach this expression? Why we okay? Why we replace I? It's the two things are different, I think. So why we just write it here? I minus j. What happened? I minus j is not equal to j. And not j. So you can you make content twice. When you content it twice, something bad will happen. Anyway, so maybe I need to write it as I less than j. I think this is it. Okay, great. Okay, it's good. Just need to watch me. And the first thing is okay. Maybe this one is right. Okay. Then we need to. Okay, we know that the need to neighboring condition is that each. This is very strong constraint. That is the people say the EQ neighboring for equilibrium condition. Harness is that each eigenvalue should, I think each eigenvalue should sit at a stationary point of. This is quite important condition. If you just want the the distribution as a stationary point globally. That is not right. You just do something like what I have done here. You got nothing. You got nothing. Okay. But if you impose this stronger constraint, then you can figure out the relationship between the density and the potential V. Okay, that's great. So this should be the stationary point of the effective the fact fact potential. Okay, so we can write the discrete sorry we can write the model as a continuous approximation. Yes, we just change the discrete eigenvalue to the continuous version. The continuous version for this term, need to write it. That is log. We just fix lambda I. We just fix lambda I. Okay, for a certain lambda I, which to make it more obvious, we just to denote it as x, then it is L V x minus. Here should be I less than j. No, I less than j. It's a certain I. Certain I. It is another eigenvalue is not equal to x. Okay, log x minus lambda square. It's j. Okay, yeah. Sum over all eigenvalue. When you sum over all eigenvalue, it's just an integral. Okay, it's just an integral. It is x minus it should be lambda, so lambda, d lambda. Okay, this is the case. Maybe I still have a program from what to what. From here, this one to this one. I found something may be wrong. I don't know why. Why the things change? This is I minus j. This one. So let me see. The situation appear here it should be. Let me consider L equal to 3. It is 1, 2, 3 to 3. It's just a three situation. But here you have 1, 3, 1, 2 to 1. The two things are the same, but they appear twice here. So I'm very puzzled about here. What happened? Why the two things are equal to each other? I don't know why. Let me see. What happened? I don't know why. It comes twice. If it comes twice, now what can happen? So the log twice, so I think there may be some extra factor, but it doesn't happen. Maybe it doesn't matter. I just see maybe it doesn't matter. So maybe they also have made a mistake here. Anyway, it doesn't matter. Okay, and I assume that this equation is right. This equation right that it should be how to say a stable point. A stable point means that the partial x equal to 0. Okay, it's a very strong constraint. Then we normalize it as L, just denote those 0. Then that is the derivative of V equal to the integral over x minus lambda d. Okay, that's great. Oh, sorry, you don't need to forget the square here, so you have 2 This is a vector. That's great. Yes, for this one. Here is something we need to comment. That is, in the original form, that is in the discrete form, we require that I is not equal to j. Okay, this is quite important. So here, when we write this as integral, we need to uh, expose the condition that is x equal to lambda. So this integral should be understood as the principal value prescription. I need to write it. It should be understood as principal value prescription. Now what can I get? This equation very important. I need to box it. This one. Okay, what can I get? What can I get? Let me see, take why I and what I need to know. And as before, we have another important equation. That is this one. They look so similar to each other, so we can maybe we can write v prime with the derivative of the potential v use r. So let me see. We need to. I can write it. Maybe I need to copy it. Copy it. Then we can see it. This one. So due to this integral is understood as the principal value, principal prescription. So we need to say underline it. So we need with a character p to denote that we just take the principal value of the integral. So 0 and this x minus lambda. And on the other hand, we know that Rx its definition is just integral. X lambda. Okay. You need to avoid the case that x equal to, and here usually means x should not equal to lambda. So we can consider shift x with a small imaginary part. That is that x to x plus minus epsilon. So we take the principal value. So the v prime x equal to r x plus epsilon plus r x r minus epsilon. Okay, minus epsilon. We need to take the ensemble average and take the leading order. That is because notice here we just denote this thing is definition as though is an operator, okay, of L, and take the ensemble average. Okay, it's a simple average. For to the leading order, we know that R. We need to refer to the genius expansion. The genius expansion told us R, that is R x1 x n, okay, equal to R g xn x1 to xn over L to G plus 1 minus 2 sum of G. Okay, so the kneading order is just that we need to take kneading order. Let me see. The kneading order, let me see. That is G equal to 0 and equal to 1. So it is of the order L. That's great. Yeah, great. What can happen? Did I made a mistake? No. This is the definition good. This one is this one. Okay. This one. And V prime equal to, we notice the definition. Here we have denoted with L. So we take the kneading order. Take the kneading order, we have, maybe we can use this one. L to infinity. It should give us R0, 1. This x plus epsilon minus R 1 x minus epsilon. Okay, that's great. Here's what we did. Great. Then it seems that we know this thing. This thing is what we have known. So maybe we can know this one. It's plus. Oh, sorry, it's minus. It's plus. Okay, this is a plus, not minus. So you need to consider how to use it. Then here we use a very smart trick. That is, we need to make use of the residue series. What have I have? Maybe I need to do other things. Oh, I'm back. We need to use a very clever trick. We consider a special case, not so special maybe. We consider, just assume that the zero lambda is a function, okay? It's a normalized function. Should I want to plot it, plot as a function. We assume that it start is a point called a minus, and with plus a plus. It's a continuous function from here to here. And the other regions, its function value is 0. Okay. Then we can consider what? We know that though 0, its definition is just I just write it. We have derived the equation, but it is 1 over 2 pi I and minus 1. Okay, and it is R1 epsilon minus a plus. Sorry, that is lambda. Sorry, lambda plus epsilon minus 0, 1 lambda minus epsilon. Okay, this is what? This is a discontinuity. It is discontinuity. What is this one? Maybe. That is discontinuity across the x axis. So you know that this region there is no discontinuity. This region is no discontinuity. So we need to construct a function that has the branch cut from a minus to a plus. We need to construct a function. This branch is a branch cut. This function is what? It's quite easy to construct it. That it is square sigma x is x minus a minus x plus a positive. Okay, this one. Then what can I get? Then what can I get? Then we know that this for the north side of the branch, for the up side of the branch cut, we take the value that is x plus I epsilon, and for this side we take the value x minus I epsilon. Okay, that's great. That's great. Good. Good. We consider x is away. Sorry, away from the branch cut. I need to close. Right. We need to consider a special x. The x can be taken as a complex value. X can be a complex value. So x going to c will be here. Here. Then we consider the residue series. It's quite easy to get it. That is, sorry, mistake. 0, 1. We just denote as e. Okay. Anyway, it's quite easy. Then we just integral the small cycle around the point e. Okay. And take a residue to I. Okay. Then we need to construct a single pole at e. Okay. Then we write the function here. Here we can multiply some other function. That is, the function should be analytical at the point e, but it can have other branch cut. Okay, this one has a branch cut like a minus, a plus. The contour is like here. Then you can do the contour deformation. The contour deformation will give that here, then it should be this one. Contour deformation. We need to take it to be the anti-clockwise. So we need to choose this. We need to choose this. This contour denoted as C. This is branch cut. So it should be minus over the contour C, the lambda 2 pi I R01 lambda minus E. There is a squared sigma E minus sigma lambda. Great. What can I get? Let me see. What can I get? This integral. I can get. I can get nothing. I think. No, let me see. we take the integral from here to here, okay? We see that the direction with the contour is different. It just opposite to each other at the upper side and the lower side. So this thing should equal to this point minus this point, I think. But we know that v prime is the sum over v prime is sum over the r value r01 of the two side value of the of the boundary card. So how to transfer this integral of the of the, I think so. Let me see. Oh, that's easy. That's quite easy. We can times half over here. Then we can split this function to two pieces. That is two pieces. That is two contour. Okay. Then we let me see. Two contour. Contour. This one should sum over this one. But I don't know how to do it. There's nothing to do it. Nothing to do it. Contour. Minus is plus. Sorry. Okay, I made a mistake. You need to notice that. You need to notice that the sign is encoded in the definition of the path integral. Okay, so we need to consider that we need to interpret the path continuum as to sum over all values from here to here. No, I don't think so. It's not right. This one, the dz is like this one. And from this part, the dz has the opposite side. So you cannot sum over it. You need to use the function value at this point to minus the function value at this point, not sum over them. Not sum over them. So, but the paper just says that the final result is just this one, which will makes me quite puzzle. A prime lambda minus e square e. What happened? Let me see what happened. We need to notice that this one is r z1 a plus. Oh, I know the reason. I know the reason. That is from this picture. From this contour, C is not a very it's not it can be a finite contour, which means that it can be arbitrary. It can be very arbitrary. This is C, okay? Nothing happened. It's C, and we know if this point, if this point we can just name it as G, if this point is not located at actual exactly at the branch cut, then we know that this point there is no discontinuity. There is no discontinuity. This is the key point. And here there's no discontinuity. Sorry, discontinuity. There's no discontinuity. So at this point, we can just write R01 x equal to yes, it's equal to this one. Okay, it's just a replacement. No other things, because our control doesn't occurs the branch cut. So there is this discontinuity. Okay, that's great. Okay, you may think that's great, but we still don't know we don't know the value of a minus and a plus, so we need to figure it. That's quite easy. We can evaluate the function 0, 1. Okay, sorry, this one. We consider for large E. For large E, you see this. For large E, and this is a small contour. It is very, very large. Lambda, that is the next one. Minus lambda. What is this? What can I do? On the definition, I don't know if it could do this one. I don't know how to know the asymptotic behavior of R. Seems quite pointy. When we need to know this, we need to use this one, and we know that the definition of v prime x is equal to 2 some integral 0 lambda this a minus lambda. Okay, for r go to infinity, for large E, then we can just drop lambda, so it will equal to 2 times E, 1 over E. So we know that for large E, R0, 1 E have an asymptotic behavior, that is 1 over E. Okay, then we take the limit that for large E we just expand the integral. How to do it? Let me see. Maybe it's not so hard. We can just calculate it. Not so hard. Maybe it's a little hard. Let's have a try. We know that maybe it's not easy. Sigma E is the definition is A minus A plus and A minus A minus. So this one we can just write it. No, just write it as something then. Not so hard. You can use the Taylor experiment directly because it is too large. Then you compare both sides. Then you have two equations to help us to locate the position of A plus and A minus. This is the whole story. Okay, that's all. I made a mistake.